Hello, my name is Juraj, and I'm going to be talking about the new methodology of prosodic analysis recently developed by our team. This is a methodological paper where I will be talking about a new method which uses deep learning-based speech synthesis as a tool to build a complex statistical model of the data in question. The method is very similar to recently presented typological inquiry of Swedish accent types, which you can find in the proceedings of last year interspeech. In this case, we will illustrate the methodology on the analysis of Lombard speech material. As we all know, Lombard speech is the adaptation of speech to the noisy background environment. We will analyze the given material from the prosodic point of view, so we will focus on the behavior of F0, duration, intensity as interacting with focus and different levels of background noise and different types of background noise. So if we want to present the new methodology, let's sort of do that by comparing it to the normal things which we as phoneticians normally do. We usually start our inquiries by getting hold of or creating, recording a corpus of speech of particular kind, in this case, speech in the loud environment. Then we extract prosodic features if we analyze prosody, which interest us from the signal, and then we build the statistical models which incorporate these particular features and are suited for the questions of interest. Then we analyze the fits we get through these models, and if we find something interesting, we report. The proposed method, of course, also follows the broad outlines of the prosodic analysis, but with several tweaks. We also take a corpus of speech recorded in the loud environment of Lombard speech, but rather than extracting prosodic features of interest, we remove all the other characteristics of the signal which are not of interest here. So we only keep the prosody of the signal. And then we build a statistical model, but slightly more complex statistical model, which is built by training a WaveNet, in this particular case, speech synthesizer on this processed signal. And then we analyze some components of the synthesis system of the model, in particular the conditioning embeddings. In this particular case, we actually train multiple versions of the synthesis and look what all of these embeddings which we're analyzing have in common. There we use the standard statistical tools. WaveNet is a speech synthesis paradigm where the synthesizer is trained to generate directly individual speech samples of the speech signal. So given the chunk of speech, the trained synthesizer processes this speech in some particular hierarchical fashion using diluted convolutional architecture. The way how the system is conditioned to generate some particular type of speech, some particular speech sound or some speech under some particular condition is done through the standard or the standard way of global conditioning. Global conditioning is implemented so that it influences the entire network's dynamics. For example, in this case, when we are presumably generating a speech as produced in 60 decibel background noise in a broad focus, this type of condition is encoded in terms of some embedding vector, numerical vector, which is then fed to the network architecture. If we want to produce the speech which corresponds to the narrow focus on a particular word in a quiet environment, then we would flood the network dynamics with this particular vector. The entire idea of the present work is that if the influence of the conditions on the signal are more similar to each other, the embedding vectors are going to be more similar to each other than when the given conditions are more different from each other. Of course, it's very important to know that this embedding layer is actually trained alongside the entire speech in the system, and is, as such, is the part of the system as a statistical model of the phenomena under question. So let's go back to our proposed methodology and let's go step by step through our data analysis. So let's start with the corpus of Lombard speech. The given corpus, which we analyzed here, contains the recordings of 12 Finnish sentences, which are all of the same form, subject, verb, object. They were recorded as uttered by 21 native Finnish speakers. Each of these sentences was rendered in one of the 3 possible focus conditions, either in a broad focus or with a narrow focus on subject or a narrow focus on the object word. The sentences were recorded at 4 levels of ambient noise, or background noise, with no noise, with the background noise of 60 decibel, 70 decibel, and 80 decibel. When there was a noisy condition, 60, 70, or 80 decibel conditions, the noise of the background noise was one of 3 possible types, or either white noise, or bubble noise, or noise, white noise low passed at 1000 hertz. All of these possible combinations would actually yield quite a vast number of recordings, but the corpus was actually sparsely sampled, and we all together worked with about 2,500 recording samples. We took this corpus and extracted what we call prosodic signal. So we extracted F0 and energy envelope of each of the original recordings, and use these 2 functions to generate an amplitude modulated sinusoidal signal using this type of a formula. The sinusoidal signal was downsampled at frequency of 1000 hertz. The resulting signal, this formula guarantees the resulting signal has the same fundamental frequency and energy envelope as the original signal, but none of its spectral characteristics are maintained. This particular prosodic signal simply captures only the prosodic features of interest, does not contain any potential noise, which might be present in the original recordings, has much lower sampling rate, meaning for the WaveNet synthesis, it allows for much longer receptive field without the increase in the network size. And therefore, it can capture long-distance prosodic relevant relationships. Let's listen briefly to the sort of original recording and the new sinusoidal prosodic signal. This would be the original recording, and this is the corresponding sinusoidal signal. Subsequently, we trained a WaveNet speech synthesis network on these prosodic signals. The details of the network design are in the paper. Most importantly, the network was conditioned by 2 conditioning embeddings. What we refer to as target embedding contains an embedding vector for each combination of focus type, noise level, and noise type, because we have 10 possible combinations of noise levels and noise types, including the different conditions for no noise, and 3 different focus times. This target embedding contained 30 conditioning vectors. The other embedding, which we call a normalization embedding, was designed to disentangle the influence of different speakers which were contained in the database. So there was a separate label for each of 21 different speakers. After the network was fully trained, of course, it was synthesis network, so it was capable of producing the prosodic signal sine waves as told by the given condition, and more importantly, perhaps for the current purposes, contained 2 trained embeddings. So let's have a look at how these 2 trained embeddings look like. So let's start with the normalization embedding. On the left-hand side, we can see the individual embedding vectors corresponding to individual speakers. These are 16-dimensional vectors, and in this heat map, the shades correspond to the numbers. Of course, we had both female and male speakers. They are distinguished by the shade here. It turns out that when we plot the first 2 principal components of this 16-dimensional vector space, we can see the clear separation of the embedding vectors in terms of the gender of the speaker. Actually, the first principal components separates the speakers by gender. If we visualize in a similar way the target embedding vectors, again, the first 2 principal components, we can see that the first principal component clearly separates the embedding vectors by the focus condition. They are, as the coloring suggests, here we have the embedding vectors for N1, narrow on subject, broad, and narrow on object focus conditions. If we recolor the embedding vectors by the ambient noise, from no noise, 60 decibel, 70 decibel, and 80 decibel, we can see that second principal components clearly captures the effect of background noise. So the first 2 principal components capture both sources of variance in the data, the focus and the background noise. Regarding the noise type, you might recall that 3 noise types were used in our database to elicit the Lombard effect. It was a white noise, low pass filtered noise, and a bubble noise. That's why we have three different embedding vectors associated with each combination of the focus condition and the noise level. It turns out that the one which is a bit further away from the other two for each of these combination corresponds to the low pass noise. As you can see, this is a very kind of consistent pattern across most combinations, apart from one, which is the combination of the focus on subject and 60 decibel background noise. There, the low pass noise is actually closer to one other noise type than the other, which corresponds to the bubble noise. Interestingly, this pattern is very similar to the pattern unearthed by the more standard analysis on the same database, where the low pass noise elicited less movement of F0 contour compared to the other types, except in the low noise level condition, where actually the effect of low pass filtered noise was more similar to that of bubble noise than that of a white noise. Now, I've shown you only one particular target embedding. For this particular target embedding, the effect of focus condition and noise level was manifested by different principal components, while the smaller, more subtle effect of noise type was manifested in terms of distances of embedding vectors within the principal component space. Now, the question is, given that training a WaveNet speech synthesizer is a stochastic process, can this pattern be repeated for multiple instances of the trained synthesizer, or were we just lucky? In order to answer this question for the effect of focus condition and noise level, we have trained 14 instances of the target embeddings, 14 instances of the trained synthesizer, and we evaluated to what level the individual principal components of the target embedding space correspond to these effects. So we actually fitted linear models with the focus condition or noise level or noise type as a predictor, and all individual principal components of the target embedding space as the dependent variables, and evaluated the degree of correspondence using the R-square, the quality of fit of these linear models. It turns out for each model, one of the principal components, one of the first three principal components, it corresponds well to the noise level, while two other correspond well to focus condition. This happened for all 14 trained instances. In paper, we also investigate the effect of noise type on the target embedding. I refer you to our manuscript for this information. Now, the new method which I have been presenting to you here in this talk seems to work. We got meaningful and interpretable results which are consistent with the earlier findings. In principle, the data do not need to be labeled. So we did not need to extract F0 values from particular words, from particular syllables. So in that sense, although quite complicated perhaps, the method can actually save a lot of labor for phoneticians. The synthesizer, of course, learns only the features which are necessary for successfully sort of reproducing, synthesizing the material. So the synthesizer will consistently learn only the strongest, most relevant effects that they are in the data. We would like to also pinpoint a couple more methodological contributions of this work. The downsampled artificial signal, the method which we used here and in some of our previous works, shows that we can actually expand the receptive field without increasing network size, meaning that we can make this type of methodology particularly suitable for prosodic analysis, where we need to see a longer stretch of the signal and only see the particular features of interest, let's say F0 and intensity, but other features of interest, perhaps voice quality, can also be manipulated into the signal if we wished so. That's all from me for the moment. So thank you very much for your attention. If you have any questions, please do not hesitate and send me an email. Thank you.